So my name's Helen David. I'm one of the tutors with Golden Braided Canopy. I am a science tutor, but I specialise in chemistry, mostly at GCSE and A-level. And today I'm going to talk to you today about one of those topics that's 100% going to be on your chemistry exam, and that is the topic of bonding. So we're going to talk through some ionic bonding, some metallic bonding, and some covalent bonding, but we're just going to cover simple covalent molecules today, okay, just because of the time constraints. So the first thing I'm going to show you then is a periodic table. Okay, let me just reduce myself there. So periodic table is just an amazing thing, okay? Everything in the entire universe is made up of atoms that are basically on that table, okay? There's about 100 different types of atoms that are present in the entire universe, and they are all there on a piece of paper that you get to take in on your GCSE exams. Now, of these periodic table, I can talk to you an entire lesson about the periodic table, but what we want you to realise from today's lesson is that you can split the elements into either metals or non-metals. Most elements, 75% of elements, are in fact metals, and they are placed on the left-hand side of the periodic table. Okay, those lanthanides and actinides, by the way, do not feature on your GCSE periodic table, but they are elements. They are still metallic. The yellow elements on that slide there, they're the non-metals, and there are very few of them, but they're at the top right-hand corner of the periodic table. The ones that are in red, we call them metalloids. They have properties of both metals and non-metals, so we're not really sure where to classify them, but for the purposes of GCSE, we classify them as being non-metals. Okay, so we would expect you at GCSE to know the different properties of being either a metal or a non-metal and where you would find those on a periodic table. Okay, so first thing we're going to talk about then is when you have your periodic table and you've got your elements and you can classify whether they're metals or non-metals, we need to know when they bond together, these elements, what sort of bonding is it? Okay, and for that you always must look at the actual formula of the compound or element that you've been given and work out whether it contains metals or non-metals or a combination of both. Okay, so if your compound contains two elements that are different to each other and one's a metal and one's a non-metal, then the type of bonding you have is ionic. Okay, so let me show you this one. Now, when we think about the periodic table, we think about these atoms, and we know from basic chemistry that all atoms want in life is to get a full outer shell. Okay, and one of the ways that they do that is through ionic bonding, when they either gain or lose electrons in order to get that full outer shell. Metals love losing electrons. Okay, that is what they do. Your really reactive metals, things like your group 1 elements, lithium, sodium, potassium, that first column on the periodic table, they lose electrons really, really easily. Okay, things like gold or platinum, for example, they don't lose electrons very well. That's why your group 1 elements are incredibly reactive, and your gold and your platinum are really non-reactive. It's just about the ease at which they lose electrons. Okay, now when group 1 become positive ions, they become +1 because they've lost a negative electron. Group 2 like to lose 2 electrons, they form +2 ions. Group 3, +3, and so on. Your non-metals, on the other hand, they're the opposite of metals. They like to gain electrons. And when you gain electrons, you become negatively charged. So your halogens, the ones like fluorine and chlorine, they like to gain just 1 electron to get that full outer shell, and they will become a -1 ion as a result. Group 6 become -2 ions because they gain 2 electrons. Group 3 become -3. Now, that's what ionic bonding is. It's the transfer of 1 or more of electrons from a metal to a non-metal. Okay, so when we think about these ionic compounds, they form these very crucial structures. And an example of this might be what I'm showing you here. Okay, so we would call this an ionic lattice. So if you've got something like put my pen on, a sodium, my pen's not working very well, and a chloride ion, put them together. Okay, sodium is obviously the metal, chloride is -1 because it's the non-metal. They form a compound called sodium chloride. Now, sodium chloride, it hasn't literally just got one sodium ion and one chloride ion. Sodium chloride is basically table salt. It's the salt you put on your chips to eat. Okay, but you can physically see those sodium and chloride ions. There's so many of them that we can actually see it as salt. What that is, if it's an ionic compound, that's the ratio of ions compared to each other. So for every one sodium, you will have 2 chlorides. If I stuck chloride with magnesium, for example, the formula of that is MgCl2. So for every 1 magnesium, I would have 2 chloride ions. But the ionic compounds always form this type of lattice structure. Now I'm whizzing it around. Okay, I'm looking around at it. First thing that's quite obvious about an ionic structure is that it's very regular. It's got positive ions next to negative, which are next door to positive, and so on and so forth. It is also 3D. Now, those ions have arranged themselves in such a way that your positive ions are attracting all your negative ions, because ionic compounds are held together by very strong electrostatic attractions. Okay, so if you're an ion in the middle of this cube here, you're attracting all your opposite ions in all directions. Okay, you can't see the attraction. It is a force of attraction. So it's a bit like when you've got magnets and you have opposite poles, they attract each other. That's an electrostatic, except we're thinking electrostatically. So these ions are held together by incredibly strong forces. So ionic compounds are always solids at room temperature because those ions are being held in a very fixed position. In order to break those electrostatic attractions and make it so that the ions can move around, and so you can form, say, a liquid, the ions physically can move around, that takes a huge amount of energy. So all ionic compounds have incredibly high melting points and boiling points, often several hundreds of degrees, if not thousands of degrees, just to get it to melt. So that's always a property of being an ionic compound. Okay. Other things about being an ionic compound is, bizarrely, they conduct electricity, but only when the ions are able to move. Now, electricity just requires that charged particles can move around. Often they're electrons, but if those charged particles are ions, positive or negative particles, that's fine too. So if these ions are allowed to move around, either when they're a liquid or when they've been dissolved in a water where the ions can move, then that means that they can conduct electricity. They cannot conduct electricity when they are solid because the ions cannot move. Okay. What else can I tell you about ionic compounds? Okay. But to be honest, I would think more about now. That's what happens when metals and non-metals get together. What happens when you go back and you look at your periodic table and we think, what about those non-metals? How did they combine together? What sort of bonding do they do? Okay, so covalent compounds are slightly different. Well, they're very different actually. Covalent compounds are when you've got 2 non-metals stuck together. Okay, now this is supposed to be the molecule of water. Now I use that word molecule. I didn't use it with ionic compounds. Ionic compounds do not form molecules. A molecule is a distinct group of atoms that are stuck together. So in water, for example, I've got 2 hydrogens and I've got 1 oxygen. And that is a group of 3, a molecule of 3. It is very simple, okay? Literally 3 atoms stuck together. Now, this is a ball and stick model, okay, I'm twisting it all around. It is a very weird shape, okay. If water wasn't that shape, there would be no life on Earth, but that's a different story, perhaps for another lesson. But we're showing the covalent bond as a stick between the atoms, okay. Now, a covalent bond, if you're asked what it is, it happens between non-metals, and it's the sharing of a pair of electrons, okay. Now, let's have a think then. Why do these atoms do it? Well, all atoms want in life is a full outer shell. And if you've got two non-metals stuck together, the way that they can do that is to share electrons. So let's take the element, let's go hydrogen, and I'm going to stick it with the element chlorine. We're going to make something called hydrogen chloride gas. Now, the first thing, when I'm presented with a compound there, both of these are non-metals. So therefore, I know that it's going to be a covalent bond that holds those elements together. Okay, so hydrogen's a bit weird. It's only got one electron. And in that first shell, it can only fit two. So here's my hydrogen atom. What covalent bonding does is when the atoms get close enough together and their outer shells actually overlap. It's a terrible circle, but there we go. Okay. Now, they overlap, and it's a bit like a Venn diagram in maths. The shared area, this bit, is the bit that's shared between both atoms. The atoms have an electrons from both of the atoms to be able to be shared. So hydrogen needs one extra electron to fulfill its outer shell because it's got one already. Okay, so hydrogen's got these two numbers. So hydrogen with its one electron, because it needs one from the chlorine, it has to put its one into the shared area too. It cannot share one from the chlorine without sharing its own. That's a rule in covalent bonding. Now that chlorine has got these two numbers, okay, so 35.5 as its mass number, but crucially, its proton number, its atomic number is 17. That also tells us it's got 17 electrons. 2 in the first shell, 8 in the second shell, and it's only got 7 in the third shell. Now that third shell can have 8, and that's the crucial number that the chlorine needs. So what the chlorine does, because it needs one from the hydrogen, it puts one of its own into the shared area, but the other 6, now I've done them as dots to show that they are still electrons, but they're different to the hydrogen ones. The other 6 go on the outside. So when I count them up, the chlorine's got 8 electrons, very happy, and my hydrogen has now got 1. And it is a shared pair of electrons, a covalent bond. We now have a molecule of hydrogen chloride. Okay, let's do another one. Let's say we've got some water. Okay, the water, the one that we just did. Again, I've got a molecule. It's got a formula. It's 2 non-metals, got hydrogen and oxygen joined together. That means it is definitely a molecule. So when we've got oxygen, now oxygen is in group 6, which means there's oxygen symbol. I don't bother putting the inner shells, they're boring. Okay, once they're full, they're boring, you just ignore them. So I've got 6 outer electrons. So I've got 1, 2, 3, 4, 5, and 6. Now oxygen needs another 2. So it's going to have 2 hydrogens that come and overlap, each one with one of the electrons, because the hydrogen gives its 1 electron into the shared area. That hydrogen is now happy, it's now got 2 electrons. So it has another hydrogen that does exactly the same. Okay, so there we have got 2 pairs of electrons there that are non-bonding, and we have 2 bonding pairs of electrons there. So when we draw it out, we've got 2 single covalent bonds, and there's my molecule of water. Okay. Let's have one more go then. Let's do the element, in fact, no, let's do the compound ammonia, NH3. Stop the video if you want to have a go. Ammonia has got nitrogen in it. as its central atom, and it's got 3 hydrogens. Nitrogen's in group 5, hydrogen has got 1 electron. Stop the video, have a go yourself. Okay, so nitrogen, because it's got 5 of its own electrons, it needs 3 extra. Well, that's quite handy because it's got 3 hydrogens. So what it does is 3 of its 5 go into the shared area. So there's another 2 on the outside that aren't being shared. And hydrogen puts its electron to be shared too. The hydrogens are all happy. They've got 2 electrons in their outer shell, very happy. And the nitrogen's still got 8. So there we go. Okay, now, important things about being a covalent molecule. Covalent molecules have no charges. They do not conduct electricity because electricity requires charges, remember. Covalent molecules they tend to be gases. There's a reason for that. That's to do with their intermolecular forces. Okay, I'll come on to that in a second. And like I say, covalent molecules, they are between when you've got elements that are non-metallic joined together. Okay, now simple covalent molecules do tend to be gases at room temperature. They've already boiled at 20 degrees. Okay, very simple ones like hydrogen. Hydrogen's boiling point is something like minus 269 degrees C. They are incredibly low. Very, very different to your ionic compounds. The reason for that is, let's think about if I take water and I turn it from being a solid into a liquid. That is called melting. Water is still water though, it's still H2O. If I apply more energy and I boil that water, I turn it into a gas. Okay, it's still H2O though. So we are doing, when we melt something, we are literally breaking up whatever's holding those solid water particles together. And when we boil water, we're breaking what's ever holding those liquid water molecules together to turn them into a gas. The water itself doesn't change. And that's because what you're doing, if you've got some H2O, say as a liquid, okay, and there is a force of attraction that's holding those particles together. Now, we call that an intermolecular. Inter means between, and molecular obviously means molecules. So it's intermolecular forces. They are very, very weak. And in fact, when you boil water, you're breaking all the intermolecular forces that are holding those liquid water molecules together. Okay, so let me show you, say, something like this. So this is carbon dioxide. Carbon dioxide is a gas at room temperature. So if I've got my carbon dioxide molecules, okay, they've got very, very strong covalent bonds holding those atoms together in the molecules, but they're very weak intermolecular forces in between. And when you boil or melt, you are not breaking the covalent bonds. That would take way too much energy. You are breaking the intermolecular forces holding those molecules together. So a big thing about if you have details in a question that say what sort of molecule is present, always look at their melting and their boiling points. Okay, so let's have a look at this example. Okay, stop the video, pause it, have a look, read the question. So give the letters of the substances in the table that have a simple molecular structure. So what we need to think about is if it's got a simple molecular structure, that means it's going to be easy to boil. It's going to have a low boiling point because it's going to have covalent bonds. The word molecule tells me it's covalent. Okay, so it's going to have a low melting point and low boiling point. These things are all relative. Okay, crucially, if it's a simple molecule, it is not going to conduct electricity. So I can get rid of C for automatically. Okay, that conducts. Okay, that cannot be a simple molecule. So I'm looking for things that do not conduct at all, whether they're solid or liquid. So actually, substance A Yeah, that fulfills it. It's got quite a low melting and boiling point, doesn't conduct. B is a simple molecule, okay, for the same reasons. And the last one, I think, would be F. Very low melting points and boiling points, definitely isn't conducting, definitely a simple molecule. So A, B, and F. Okay, have a think about those words that you'd fill in as well. And stop the video, and then we'll talk it through. So the answers to that would be simple molecular substances are substances made of molecules. A molecule is a particle made from atoms joined together by covalent bonds. A covalent bond is two shared electrons between two atoms. Simple molecular structures have low melting and boiling points. This is because there are weak forces between the molecules. They do not conduct electricity because molecules are not electrically charged. They are neutral. Okay, right then. Now, people often struggle with identifying whether a substance is ionic, simple molecular, or in fact, could it be neither? So have a look at these. You've got to tick off, looking at their formulas, which one is which. Is it ionic, simple, molecular, or is it neither? Okay, stop the video. Right then. Well, actually, when we look through it, you always start by looking at the formula. Is it a metal and a non-metal? So that first one there, calcium and fluorine stuck together, the fact that I would call that calcium fluoride, the fact it says "ide" at the end, is usually a giveaway that it's ionic. So that one would definitely be ionic. Whereas NO2, well, nitrogen and oxygen are both non-metals, so it's simple molecular. Okay. AU is weird because AU is actually gold. Now, gold is an element, so it's neither. So all the ones that are elements, the argon there at the end, AR, that's neither, okay? But, again, look through your compounds. If it is a compound made up of different elements stuck together, if those elements, one's a metal, one's a non-metal, it's ionic. If they're both non-metals, it's simple molecular. So hopefully you got all of those. Okay, now this brings us on to a nice part. Let's think about, well, if you've got something like gold or silver or lithium or potassium, if you've got a metal, well, what sort of bonding is going on in there? And the answer to that is it's metallic. Okay, so metallic bonding, clue is in the name, often is in chemistry. Metallic bonding is when you've got metals. Okay, metals. Now, we all know about metals. Metals are really hard. They're tough. They're shiny. They're lustrous. Okay, that's a posh word for shiny. They're sonorous, so they ting when they're hit like a bell does. They're malleable, okay, which means they are hammered into shape easily. But a crucial thing is they conduct electricity. They conduct it really well, whether they're a solid or a liquid. Okay, they're really quite special, and that's due to the bonding that's going on. So it doesn't matter what metal it is. This could be sodium, potassium, lithium, calcium, strontium, copper, zinc, whatever it is, it's got this bonding. They are all metal, all solid, sorry, at room temperature. The only one that's an exception is mercury. Okay, mercury is weird. It's a liquid at room temperature, very odd. That's the one that's used in thermometers. It's got really strange bonding going on. So every other metal though is a solid. So when we draw a solid, we've got those particles, they're touching together because the forces of attraction are very strong, holding those particles together. Okay, now metals are strange. That's just not metallic bonding unless I put a plus sign in each of those atoms. So they're not atoms anymore, they are cations, positive ions. Okay, so I have a nice regular arrangement, okay, of positive ions. Now that's a bit weird because if I put positives next to positives, my overwhelming feeling is they're going to repel each other. And really they should, but they don't though. Because they've become positive, it's because their outer electron is now whizzing around, delocalized. Okay, that just means that the electrons there don't belong to a particular atom, they can move around. So we say that they're not local to an atom, they are delocalized electrons. And so you've got these positive ions that are not repelling each other because they're all being attracted to these negative delocalized electrons. The delocalized electrons are like acting like glue, keeping those positive ions together. Okay. Now, it's these delocalized electrons that crucially can move. Because electrons are negative, that means you've got a negative charge that's able to move. So if you apply a potential difference, if you make one side negative and one side positive, the electrons are all going to flow towards the positive side. Okay, that is electricity. Electricity is just literally the movement of charge. So metals can conduct electricity because their delocalized electrons move and carry their charge. Okay, so they're really quite exceptional. So quite often in GCSE, it'll be worth 3 marks and it'll say, describe the type of bonding in copper or silver or sodium. And what they're wanting is that diagram. Okay. Now, because the electrostatic attraction is very strong, metals tend to have very high melting and boiling points. Because if you're going to break those attractions, that's going to take a lot of energy. Okay. And the other reason, we mentioned the word malleable before. Malleable just means if you hit a metal, you can hammer it into shape. So if you hit a metal, if I lodge that layer there, if I move it, okay, to the right, all I'm doing is shifting positive ions over positive ions. Okay, there's still delocalized electrons whizzing around, holding those positive ions together. So you can shift the layers across each other. The layers slide across each other very, very easily. And that's why metals are really good at being hammered into shape. Okay, what about then? Let's go with having a go at this question. So a little question for you there. You can stop the tape and have a go. Okay, so part A, aluminium oxide. Aluminium oxide is made up of an ionic structure. Okay, it's got metal and a non-metal. And the formula is literally just telling me that the ratio of ions is 2 aluminiums for every 3 oxides. Okay, formula CO2 in part B tells us that I've got 1 carbon and 2 oxygens. But because it's a simple molecule, there is literally 3 atoms in total. It's 1 carbon, 2 oxygens, 3 atoms inside that molecule. Now C, aluminium oxide has an incredibly high melting point, whereas carbon dioxide has a low one because aluminium oxide is made up of positive and negative ions, which are strongly attracting each other electrostatically. You've got to put in a lot of energy to break that attraction. Whereas CO2, because they are molecules, when you are boiling it, you are breaking the intermolecular forces. Now, intermolecular forces are very, very weak. It doesn't take a lot of energy to do that. They break very easily. And part D, carbon dioxide does not conduct electricity in any state. Aluminium oxide does when it's molten. Okay, so molten aluminium oxide, that's because the ions then can move and they carry the charge. Okay, whereas carbon dioxide, there are no charged particles at all. Okay, right then. Let's play a little game then, I think, to finish. Let's see how we can do with these. So in my lessons, I do a lot of games. So let's see whether you can put these into their groups by just looking at their formulas. Okay, so you can stop the video and have a go before we do it together. Okay, so if I'm faced with these things, if I've got to work out if something's ionic, covalent, or if it's metallic, you've got to look at the formulas. That's massively important. So if I'm looking at metallic, I'm looking for anything that is a metal. So magnesium is definitely a metal. Zinc is definitely a metal. Copper is metallic. Okay. Calcium, bit weird that, but it is definitely a metal. All of those, except copper, are silver coloured, by the way. There's only two metals that are not silver coloured. Vanadium, there's a weird one. That's a transition metal. That's definitely a metal as well. Sodium, definitely a metal. So all of those elements there will all have metallic bonding. Okay, I'll come back to that in a sec. Anything that's got a metal and a non-metal is ionic. So potassium and sulfur getting together, sulfide there, ionic. Okay, magnesium and iodine together, ionic. Okay, what else can I see? I've got calcium hydride there. That's a weird one. Okay, that's definitely a metal and a non-metal, as is sodium chloride, as is silver bromide. Excellent stuff. Sodium oxide. Okay, potassium, I've missed that potassium there. That's definitely a metal. I've got zinc oxide, definitely ionic there. Two elements that are opposite to each other. Okay, lithium fluoride, ionic. Very good. Right, something like CH4, what we call methane, that's got two non-metals stuck together. Definitely a simple covalent molecule. So all of these, hydrogen sulfide, even though it ends in sulfide there, okay, a bit weird, but definitely two non-metals stuck together, as are those two. Chlorine gas, definitely that. Hydrogen chloride, there we go. Definitely those. Now, these are quite small. Let me just move that so I can see. Now, conduct electricity when molten or dissolved in water. Now, I'm going to say that that's ionic. High melting point due to electrostatic charges between ions, definitely ionic. Low melting point due to weak intermolecular. Intermolecular is your clue there. Don't conduct electricity at all. Same, that one there, covalent molecules. Conduct electricity regardless of state, definitely a metal. And then high melting point due to strong electrostatic attractions between the cations and your delocalized electrons, definitely metallic. Now, hopefully those are right. Excellent. And we got all of them right. Okay, so there's a bit of an introduction there of some different types of bonding. I hope you found that useful. If you'd like any more lessons with myself or any of our other tutors, please do get in touch with Richard or Alison at Golden Brain Academy. Thank you.